There we go. It's a distinguished scientist to be the lecturer. The Biard lecturer interacts extensively with the Caltech community, gives a technical seminar and also a physics colloquium. And this year, the Biard lecturer is Soonwon Choi of MIT. Soonwon is to Caltech. After growing up in Korea, he was a Caltech undergrad who got his BS degree in 2012. Soonwon took 3 classes from me and also did a successful, and I was not the only member of the Caltech faculty who was impressed at the time by Soonwon's ability. In fact, he was appropriately recognized as a graduating senior with the Richard P. Feynman Prize in Theoretical Physics for outstanding achievement in theoretical physics by a Caltech undergrad. By that Caltech success, Soonwon went on to Harvard, where he in Michalukin's group. He was a Miller Fellow at Berkeley and then joined the MIT faculty in 2021. Soonwon's research interests are quite extensive. They span issues in condensed matter, matter far from equilibrium, atomic molecular optical physics, and quantum information. He has had a very productive collaboration with Caltech scientists, especially Manuel Endres's group, with whom Soonwon developed a pioneering protocol for benchmarking analog quantum simulators and new ideas about characterizing the high-order statistical fluctuations of chaotic quantum systems through the theory we now call deep thermalization, among many other things. Soonwon is also actively pursuing, as we'll hear today, new ideas in quantum metrology. His IQ seminar is on a topic, which is quantum protected phases of matter. But today we'll hear about quantum computing enhanced sensing. So please join me in welcoming Soonwon.
Thank you so much for nice introduction, John. I was pretty confident, happy, like up until like 5 minutes ago. Now I'm extremely nervous. Now I see all the professors, like my academic advisors, my research advisors, the professor who taught me how to write, like scientific writings, the postdocs who taught me how to enjoy like physics research, like people who taught me like statistical physics. So giving a research talk in front of all those professors, I'm pretty nervous. I take it as my extremely honor that I give a colloquium talk in my undergrad school. So I take it as an honor. To those who, like maybe some undergrads in this audience, I want to tell you a story. In fact, even though I'm giving my colloquium talk like for the first time here, this is not the first time I'm giving a talk in this particular room. Because I have taken Physics 5, and the final project presentation was done in this room. So to those who hope you, like undergrads, take that opportunity wisely, because perhaps the next time you can give a talk in this auditorium will take more than 10 years since you graduate. Anyway, let's get started. Today I'm going to talk about one of the projects that I'm most excited about, quantum computing and sensing. Before anything, I would like to acknowledge the collaborators. So Richard Allen is a graduate student at MIT, and Francisco Machado was a postdoc while this work is done. Now he's at the Technical University of Delft. And Ike Chuang is my colleague at MIT, famous for quantum informations. And also Robert Huang, you must know. So at the time he was visiting MIT, now faculty here. So let's get started. Perhaps one of the most interesting aspects of my field is that it is such an exciting time for quantum information science. Across different platforms, across industry and like academia, we are making very rapid progress. So this is an already outdated photo that I took from Quantinuum website, which is a company. And they developed the trapped ion systems that operate quantum gate with a very high fidelity. This is a picture that I took from a paper published by Harvard-MIT collaborations where you move atoms and their degree of control and manipulation is so advanced, now they can routinely implement logical circuits with the error detections or sometimes error correction. This is the photo that I took from my colleague here, Manuel Andres, where you demonstrate each dot here is an atom capable of encoding 1 qubit. So you can encode 6,000 atoms, like 6,000 qubits reliably and they demonstrate that you can do that without compromising the fidelity of their single qubit manipulations. So across the quality and control and size, future is very bright. But I'm not an experimentalist, so let's talk about something relevant for theorists, or not only theorists, for all of us. Given this excitement, what should we do with these quantum computers? So many people will have their own answers to this question, but then I'm going to ask you the follow-up questions. Is the task that you want to do useful or not? For a certain task, it might seem very useful, but sometimes it's not useful for a long time, but useful only for a few occasions. For example, breaking crypto system. Over long term, what we need to do is change the crypto systems. Therefore, factorization is, in my view, is not continuously useful, but even though it has a high impact to the society. And finally, we want this application to be something that's quantum. In some sense, quantumness is used so that there's no alternatives. If we impose all three conditions, there are examples. However, there are not many examples, especially not many examples where we can confidently say we for sure enjoy some advantage out of quantum systems. So today what I'm going to do is I would like to share my viewpoint about what we should do if you have advanced quantum technology. And that's quantum sensing and metrology. Partly because in some sense, even the beginning of quantum computing has been originated from while developing technology for sensing and metrology. Indeed, when I was in my grad school, we still improved our ability to detect gravitational wave and eventually detected the first event in my 2016 gravitational wave detections. Not too long ago, a couple of years ago, we also reported the detection of nuclear transition, optical nuclear transitions, which open up the next generation atomic clock based on nuclear transition. Not only what happened in the past, looking forward, we know our universe is largely occupied by dark matter and dark energy, but we have never directly detected them. Perhaps in order to detect them, we need to develop the better sensing technology, and that will literally open up another windows to look into the universe. So even though the sensing is a very diverse field, as a theorist, I'm going to simplify and present most simplest possible theory of how quantum sensing works. And that's Ramsey interferometry. So drastically simplifying, let's consider our aim is to estimate the strength of the magnetic field pointing along z directions, coupled to my spin-1 half particles as z operator in this way. We ask how small magnetic field you can detect and how precisely you can detect that kind of questions. Of course, this does not have to be the magnetic field, but I'll just share the intuition based on magnetic field. It could be any parameter of the Hamiltonian. This problem, the optimum solution is known. First, prepare a superposition of spin up and spin down, which is in Bloch sphere, something pointing along the equator. And then evolve under the Hamiltonian with the unknown parameter b for time duration t. Then it'll precess at the Larmor frequency b, accumulating the angle theta, which is b times t. So this theta now encodes information about the strength of b. Now what we do is we rotate the spin such a way that this phase information is translated to the population information and measure spin up versus spin down. Each measurement will give you probabilistically up or down But repeating a few times, we have a rough estimate of probability measuring up, probability measuring down. Based on that estimate, we can deduce the strength of B. In order to detect B, the angle should be order 1 for the few repetitions. Therefore, the minimum detectable signal, the weakest signal we can detect, scales by the relations B times T being some order 1 angle. Therefore, the minimum detectable signal B min scale as evolution time. So longer time, longer coherence time we are given, we can detect a smaller field. So this is for the single particle, but what if we have n particles? N particles, and then how the sensitivity scale? In fact, just repeating the experiment, just doing the experiment in parallel, we can reduce the statistical noise of estimating probability of up and probability down. Therefore, we have an improvement of factor of square root of n by reducing the variance. And this particular scaling is sometimes often referred to as the standard quantum limit. This is not the most conventional formula, but I'm simplifying the settings for now. But interestingly, it turns out if you prepare entangled quantum state, sometimes you can treat all n spin-1/2 particles as if one superatom, especially if you prepare the GHG state, like down, 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 and up, up, up in superposition. They behave as a single superparticle where the matrix element is multiplied by a factor of n. But you do not enjoy like the statistical averaging. So relatively, you have a the improvement by another factor of square root of n. So you can think of it as n times sensitive single particle. That's the factor of n. And this particular scaling is often called the Heisenberg limit. So there has been a lot of efforts to achieve this Heisenberg limit. Sometimes we try to use error correcting code so that we fight against error and still achieve this Heisenberg limit scaling. Sometimes doable, sometimes probably not doable. Sometimes we use quantum circuit to variationally figure out best quantum state that handles a trade-off between the unwanted noise and sensitivity. Sometimes we use ensemble of sensors where we do not have a full control, but the ensemble control. Still, we use a collective behavior and quantum materials to have a scalable way to achieve entanglement-enhanced sensing, and many more. But I'm not going to talk any of these because these are not in this talk. Rather, I'm going to ask different question. Is there any qualitatively different sensing advantage from what I just described? I'm not going to talk about entanglement-enhanced sensitivity, but something else, especially by combining quantum computer together with the quantum sensor. So that's my introduction in today's talk. Roughly 4 items: uneven distributions of time. I'll talk about AC sensing and its algorithm, its experimental realizations, and some discussion and outlook. So let's get started. So specific problem that we are going to address and then argue that quantum computing is useful is broadband AC sensing. Imagine our goal is to detect a weak oscillating signal at the unknown frequency as quickly as possible. So Hamiltonian is the same, except that the B field is time dependent. B cosine omega t plus phase. B is a strength, amplitude, that's unknown but very weak. And omega is frequency, that's unknown but otherwise is drawn from a certain range of frequency that's known. So the range is known but otherwise unknown. Phase phi is some number fixed but unknown. It's from 0 to 2 pi, randomly picked. I don't know. So this problem is characterized by 2 parameters. One is what is the minimum detectable signal that defines sensitivity B min. The other one is a range of the frequency over which you need to find the signal. Our goal is to tell whether the signal exists or signal does not exist as quickly as possible, measuring the physical world clock time. So one example, that's our problem. So that's what we call the sensing time. And the sensing time, the physical world clock time, in principle depends on the target sensitivity and the bandwidth. I want to minimize that. This is practically useful task. It's not exactly the same as gravitational wave detections. However, you can see some similarity in a sense that we are trying to detect unknown signal. Dark matter detection for a certain models of dark matter, namely called the X-ionic dark matter, the mathematical formulation is actually quite similar. And NMR and quantum clock, they are somehow related to this type of AC sensing detections. So this is practically useful. At the same time, this is a conceptually important task. From a theory point of view, especially the complexity point of view, this is the simplest possible example of time-dependent Hamiltonian parameter learning. And the relevant question is fundamentally, what would be the complexity? What is the fundamental hardness of solving this problem? And what would be the optimum algorithms, etc. And those would be the context of solving this problem. So how do we solve this problem in conventional approaches? Let's talk about existing conventional approaches that's actually being done for a certain experiment, for example, search for X-ionic dark matter. So to understand, let's first assume, what if we knew the frequency of the signal? So I know the frequency of the signal. I try to do the optimum solutions. You polarize into equator, evolve under the signal, and it'll accumulate. The problem is it'll accumulate angle theta, but angle theta is the integral of the B field, which is changing over time. So on average, it'll average it out. So it'll just oscillate and never accumulate for a long time. So if you just accumulate, it doesn't work. However, you can easily fix this problem. Because I know the frequency, I apply rotation of 180 degrees, like so-called the pi pulse, of my sensor particles every time signal is crossing zero. Then if you change your frame and instead of rotate the spin, but assume the signal is rotating its sign, the effective signal looks like this. So now integral is non-zero. So simply by periodically applying pi pulses, 180 degrees, and pulse-to-pulse separation determines the frequency that we are detecting. So the TP, pi over omega, where omega is the target frequency, we can achieve the sensing. And turns out we can rigorously prove this is the optimal way to detect the signal. Similar to previous Ramsey, minimum detectable, the sensitivity, the amplitude, scale as 1 over t. T is the evolution time. And at the same time, even if the target frequency is not perfectly resonant or aligned with the, what's set by the pulse-to-pulse duration, as long as the deviation is smaller than Fourier limit of my sequence, like 1 over t, you can still detect it. So we are sensitive to the small bandwidth delta omega around the target frequency you want probing. But we solve problems where we don't know the frequency. So conventional approach is divide the whole range of frequency into the smaller bins, each of size small delta omega, and probe one at a time. Okay, you check whether signal exists or not. If it does not exist, move on to the next, and then scan. At some point, you detect the signal. Lucky, maybe Nobel Prize. Or if you don't detect at all, you conclude, okay, the signal does not exist at the level of sensitivity B min. This approach, the total time to scan from over the entire frequency range can be estimated by just computing the number of bins and time for each sensitivity, and that scales as this: bandwidth over sensitivity square. And that's the time it takes to solve this broadband AC sensing problem in this conventional approach. What if you have n particles? If you have n particles, one approach is take each particle responsible for the different frequency bin and perform in parallel. Or put all the particles and then use a statistical enhancement to achieve the better sensitivity for one bin and then scan over. Doesn't matter. They have exactly the same the sensing time scaling, bandwidth over number of particles times sensitivity square. Situation is slightly different if you use entangled particle like superatom and then scan over, then we can improve by a factor of another n. So the sensing time scales as bandwidth over n square and then B min square. Turns out, for the variety of variations of the platforms, we can write down the sensing time in these two factors, 1 over n B min, which is basically time for each bin. The second factor is the number of bin that you need to scan over. So I often write in this way because that's easy to parse the equation. Turns out for a variety of approaches, the technical details specified in the paper, the conventional sensing time scales in this way. And it seems like this is one fundamental limit for a class of algorithms. One way to look at this result is the following. Let's imagine we are given total fixed time. Maybe PhD takes 6 years, so like 6 years. And then ask what would be the sensitivity and bandwidth landscape we can accomplish within this fixed time. If you have n particles without entanglement, you define the line. So to the top left, that means not so good sensitivity regimes we can achieve. But if you want to try to minimize the sensitivity or probe the large bandwidth, you cannot go beyond this line. But if you entangle them, we can lower this line and define the new domain by improving by square root of n. And so this is a regimes that you can prove with the standard quantum limit and Heisenberg limit. And what I'm going to do now is I'm going to explain how to improve this by quantum computer. I'll first talk about construction of algorithm, and then we'll analyze a little bit in depth of how much advantage you will get and where it's coming from. So by this point, any questions? Okay, so let's move on. So first, what do I mean by quantum computing enhanced sensing? So I'll consider the following settings. For now, I have a universal quantum computer made out of many unbounded number of qubits and sensors. I'm going to assume sensors are always put in an entangled state, maximize the sensitivity. I'll just therefore treat them as if I have a single particle, like GTG state, like some superatom. And then I'll consider all possible sensing scenario where I can apply entangling unitary between my quantum computer and the sensor particles. And sensor particles are exposed to the signal. And then I can apply another entangling unitary between the sensors and the computer. I'll assume that the speed of the gate is infinitely fast. So the physical time of the gate is like 0. And also, I'll assume the duration between the V1 and V2 is taken to the limit 0. That means signal exposure and then gate are applied almost simultaneously, continuous control. And I do that simply because I'm interested in the fundamental limit coming from the weakness of the signal. I'm talking about the fundamental limit of total sensing time, ignoring all the control overhead. And that's the settings we are going to consider. In these settings, we were able to obtain a couple of results. And one of the results is developing a particular algorithm that we call quantum search sensing. And quantum search sensing can achieve it can solve this the AC sensing problem where the sensing time scale is in this way. So I wrote down the previous scaling here, where we basically put the square root on the number of frequency bins for the reasons to be very clear later. Okay, so this is our algorithm, and I'm going to explain algorithm later. And we obtained the second result. Turns out we can prove that no matter how you do, as long as quantum mechanics is true, then this is the best you can do. There's no algorithm that solves this AC sensing problem faster than this. Therefore, we gave a name. We call it Grover-Heisenberg limit. Yes, question?
Oh, back to the previous slide.
Yes.
So the previous one, conventional, had 2 ends downstairs. So why isn't that better? When you make n large?
So we are working in the large bandwidth regime. That means what's inside the square root is always larger than 1. So in fact, in this, here I have a ceiling function to indicate that it should be integer. Yeah, that's right. So broadband case, yes. Yes.
The argument of your order of, isn't it changing units between those? So it's hard to.
Sorry?
It looks like the argument of your order of function is changing units.
No, because this is a frequency and unit of energy, and B means a strength, which is a unit of energy. So this is unitness, rightfully, because we are taking the square root. So this is unit of energy, so this is a time unit. That's right. That's right. Okay, good. Any other questions? So put into the context, we can plot it in this diagram, parametric diagram. So for the fixed total time, Grover-Heisenberg limit define the different scaling of a line. So we prove that this regime is not achievable, so it's impossible. And our algorithm basically saturates this line up to some logarithmic correction. So that's the main results. So what I'm going to do, so in this diagram, what it means is for the fixed bandwidth, we can improve sensitivity compared to the Heisenberg limit. Or for the fixed sensitivity, we can improve the bandwidth. But I want to emphasize this is a two-parameter problem rather than a single-parameter characterizations. So for the remaining time, I'll talk about how to construct these algorithms. So main idea is the following. I'll look at this problem as a search problem. Indeed, once you divide the frequency into different bins, we are trying to find which bin contains a signal if the signal exists. But this search is something that's known that quantum computer can do much better than classical computer. So let's talk about search problem. For now, let's step away from quantum sensing and talk about search. Suppose there are n boxes, and I promise you one of the boxes is special. You are asked to find it. Otherwise, I give you no information. And there's no smart approach. The only approach is open the box and check if it's special or not. It's empty. Okay, maybe next to the box, next box, open the box, check if it's special or not. At some point, you will be lucky, or open the box and it contains a key. So, I found the marked element. And this approach is the best approach because there's no information at all. So you need to do at least, on average, n over 2 query. You need to open at least half of them because, you could be lucky, you could be like unlucky. So this task of opening the box and checking is in computer science called query. You query whether the box is special or not, and I'll refer to that term again. But turns out, this type of completely unstructured search, if you have a quantum computer, you can solve with square root of n computational step, square root of n quantum queries. That sounds almost like unbelievable or almost like cheating. Like information theoretically, you have n boxes. Square root of n is vanishing fraction of n in the limit n is very large. So how can you do that? And the answer is because we consider different settings. This operation of opening the box and checking, this query, we assume for quantum case, we can quantumly check a quantum query, assuming we have a quantum oracle. So let's spend some time thinking about what this quantum oracle means. Quantum oracle is a unitary operation. I'm going to assume I can apply this unitary in my quantum computer. And what does this unitary do? This unitary takes as an input one lag, which is an index. Maybe you represent the binary number 0, 1s, representing some integer k, they enumerate different box. And the other one is just output lag that's initialized and say 0. I promise you, if I run this oracle unitary on this input, I get the same output for the query index part. However, my output part will flip its bit if and only if this input k was the marked element. Okay? And importantly, this is a unitary operations, and therefore we can do in superposition. If I put in a superposition state of query, the resulting state after this unitary will be the superposition, but only for the marked element you flip this to 1, generating entangled state between this input part and then output part. So this assuming the ability to run this oracle is mathematical way to formulate that you can quantumly open the box and check whether it's a marked element or not. However, I want to emphasize this is a mathematical formalisms, but there's no reason that in the real life I have access to the unitary, especially if my goal is to find the marked element. How come I can implement the unitary that changes this bit without knowing the marked element? So that's one of the criticisms of the Grover's algorithm. In computer science, Grover's algorithm and Grover speed up is important for other reasons. However, just face value of the Grover's algorithm is not believed to be practically useful because of this assumption that you can apply this unitary somehow. but I'll come back to that point later. So how does quantum search work if you have an oracle? It's pretty easy. Classically, if you open the box one at a time, the probability of finding the marked element grows linearly over each attempt. So success probability is increasing as you open more boxes linearly as an algorithmic step. But I'm going to show you that in the quantum case, you query in parallel and superposition and leverage the parallelism of quantum mechanics such a way that the amplitude of success will grow linearly over algorithmic step every time you quantumly query. But we know that probability and amplitude are related by absolute square. Therefore, if you have a linearly increasing amplitude over algorithmic step, in terms of success probability, it's going to be quadratically improving. Therefore, without having to see all n, only with the square root of n, you can make success probability to be order 1. That's how it works. The actual Grover's algorithm is very simple. So I'm going to explain in one slide. Let's prepare equal superposition of all possible possibility state. And then I'm going to apply Grover oracle and some other operation called R and O and R and repeat many times, square root of n times, and finally measure in the conventional computational basis. So how does it work? So here, the Grover oracle, or like I call it an oracular reflection, can be obtained from our oracle access, or it's a similar version of it. What it does is you take the input state, and input state can be always written as a component. That's the marked element, which we don't know, but we can understand as a component, and the rest of the wave functions. If I apply this oracle, it changes a phase only for that marked element piece. The remaining part is untouched. So that's what this oracular reflection does. I can easily construct this oracular reflection based on our oracle access. Second one, R, is what I call init state reflection. Given any wave function, I can decompose into the component that's initial state psi 0, which is equal superposition, and the rest of them, which is perpendicular to it. Similar to the Grover oracle, this changes the sign only for this equal superposition component and don't touch the other one. This R operation does not contain any information about marked element, so I can implement it without knowing the marked element. So R is something I implement. O is something we can implement if I assume having access to the Grover oracle. One note, this R applied to psi, you pick up the phase here, but the global phase is not relevant for quantum mechanics, so I can just change the phase to the perpendicular component. So I can write in this way as well, equivalently. So let's see how it works. So we start from an initial state that's equal superposition. I'm going to use this diagram. So these bars represent amplitude for each query index. I start from the equal superposition right here. So what happens if I apply Grover oracular reflection? It changes one of the amplitude, the sign of one of the amplitude. Let's say in this case, maybe the first one is marked element. And then I'm going to apply the reflection operators. What happens? Well, I want to rewrite this state as a superposition of equal superposition and what's perpendicular. And that'd be like this. We have an equal superposition and what's perpendicular, but this is sufficiently negative so that when you add them up, you reproduce this state. And then we change the sign of the second one, because that's the action of R. And the resultant state, if you combine them together, is that the first one has a little bit higher amplitude. What we do is we repeat these procedures so that after second iterations, this first element is even higher, or even higher, and we can show it linearly accumulates amplitude such a way that probability is growing quadratically. So this is how Grover algorithm works, and then quantumly you can find the marked element square root of n. So let's go back to our sensing example. So our search is now really search over boxes, but search over frequency domains. But the problem is that we should not assume we have ability to run the Grover oracle. Rather, what we are going to do is we are going to build quantum oracle because we are doing quantum sensing. So the target unitary that we want to implement is very similar to Grover oracle, except it should be made out of sensing. So we have a quantum computer that has index that enumerates different frequency bin and output 0 and also have a lag that's quantum sensors already in the entangled state. I want to design some sensing protocol, U, such a way that under this protocol and control, this index does not change, but you flip this side, the output, only if the signal exists in kth frequency beat. And I want to bring back the qubit, the sensors to the original state so I can use it for another time in the future. Okay. But this is challenging because we want to implement unitary operations. What it really means is that we allow superposition of this K. That means we are probing different frequencies in parallel. At the same time, our search is not over boxes, over continuous domain. Making it further challenging, we do not know the strength of B or the frequency. It's all continuous variable and unknown. However, somehow we need to construct the discrete output, 0 versus 1, discretely, without knowing those values. So those are the challenges. In fact, these are not only the technical challenges, but also there's a conceptual challenges. So let me illustrate one conceptual challenge. Suppose, like it's a conceptual challenge, so I'm going to assume I can do everything that I want. I'm a super theorist. There's a quantum computer, maybe in base monoblaris in Andrea's lab. And there's a quantum sensor particles, but it's a conceptual picture, so I'm going to say the sensor is advanced. So in fact, I'll put entire building, like this Heisenberg building, to be built, and assume that's a black box, perfectly isolated from the environment, and then all the researchers inside as my sensor unit. Okay, it's perfectly isolated. And then our quantum computer, or like a grad student in the Andreas group, is feeding in the target frequency to the sensors in the Heisenberg building, and then ask them to detect the signal at the frequency or not. And you can do that in superposition. So you have you consider the superposition in W, handing in the different frequency, and then inside the black box, they are handed a certain value, and then perform their best sensing, and then tell you answer or no. They perform the sensing based on assuming the frequency is omega they're given. And then, depending on the yes or no, just write down the answer on one of the output bit. And perhaps we implemented a quantum oracle. No, it's not the case. Because what happens is, we built the oracle, so we need to do something with these experimental lists. Because at this point, these experimental lists are entangled with my quantum computer. If I want to do a gain, I need to disentangle them. But how do we disentangle them? One way is just throw them away and build another building. Maybe conceptually, that's a valid approach. Some people will not be happy, but in principle. But that doesn't work, because from the moment I throw them away, of course I'll be sad, but at the same time, that means the entangled state is traced out, therefore it leads to the decoherence of my quantum computer. That's more precious. I cannot decohere my quantum computer. And this issue persists in conventional quantum computing in many places, and people invented a solution. Solution is undo the computation. You take exact same operations, but reverse it. And that operation is called often uncomputing. Okay? You copy down binary answer and do exactly opposite to prepare it back to the original state. And this uncomputing is what's necessary for quantum computing. However, it still doesn't work for our case, because every operation can be uncomputed and reversed because of unitary evolution, except the signal. We don't know the frequency. We don't know the phase. Therefore, signal might have changed their relative phase when I apply this for the second time. Therefore, everything operates exactly the same except the signal, so you cannot uncompute them. So this approach doesn't work. And we had to, so because of this issue, at some point during the project, I was like, oh, maybe global Heisenberg limit is fundamentally unachievable. Turns out we had to develop the new techniques. So what we do now, which I'm not going to explain in detail, is that instead of doing uncomputing, we design the sensing protocol in a way that you don't have to do the uncomputing. So if you're interested, we can talk. So in short, we have challenges arising from interfacing quantum sensing and quantum computers. Quantum sensors often deal with the analog signals. Quantum computers deal with the digital signals. What's missing is how to robustly connect them each other in a way that we only learn the desired informations and in a way that uncomputing becomes not an important issue. And that was a technical challenge. So and we introduced the idea called the digitization. What we do is, even though the sensing signal is analog, and oftentimes the quantum state changes in a continuous fashion to the signal, we design the quantum sensing unitary such a way the response is discretized as a function of intensity, and also it's independent of the phase of the signal. So technical ingredient, there's a set of technique we call it digitization. So there are 3 different technical ingredients. One is how to do the sensing in parallel in superposition. Second is phase agnostic sensing. Third is nonlinear signal processing to make a digitized response. So for the time constraint, I'm not going to go all 3 ideas, but let me just briefly talk about the first idea, the coherent superposition sensing. Let me recall that for the AC sensing for the known frequency, it is a timing between the pi pulses that changes the pro frequencies. So if you have a different timing, you're sensitive to only one frequency. So the response is peaked at a particular target frequency determined by pulse-to-pulse duration. What I do now is, instead of applying pi pulse, I assume a quantum computer in a superposition state, and condition on a particular state, I apply controlled knot operation. And I choose the timing such that for different conditioning state, operate conditional knot at the different time separations. In this way, we can effectively perform the different frequencies in superposition that's conditioned on the quantum state. And this is a basic idea of how we can do superposition sensing. Any questions? Okay, let's talk about quantum advantage. So, naively, it's well known that quantum advantage of Grover's algorithm is quadratic improvement. What used to be square root n is n, so the relation is quadratic functions. However, that's a little bit naive assessment of our approach, because Grover algorithm counts the time by the number of query you do, but we are performing sensing, so we should count time by physical time needed. And that's not always equal. So recall this diagram. So if you're operating here, we can have a large speed up because you can improve either bandwidth or the sensitivity. But we already see at the bottom there, when the bandwidth is very narrow, that means I basically know the frequency, then our approach does not help you. Okay? So in some cases, we have a large speed up, some cases we do not have a large speed up. So it's a 2-dimensional parametric dependence. So in fact, we can leverage this to consider the scaling regimes where the speed up could be much larger than quadratic. For example, let's imagine a sensing field is coupled to the particle, but the matrix element is known to depend on the frequency. And this happens very often in high energy physics because coupling strength runs as a function of frequency. In that case, if you assume this coupling strength scales as omega to the some power law, mu, frequency mu, depending on the value of mu, when mu equals 0, we have a quadratic speed up. But whenever the mu is larger than that, we have a beyond quadratic speed up. When mu is between 1/3 and 1/2, turns out quantum algorithm completes the search very rapidly in order 1 time, but the classical search depends on the total bandwidth. So it's so-called super polynomial separations. When it becomes larger, both tasks can be completed very fast. Second aspect I want to talk about, the origin of quantum advantage, metrological gain. In the conventional settings, it is an entanglement and their collective behavior that gives rise to improved sensitivity. However, for our algorithm, it's hard to pinpoint exactly what. Even though I said quantum computer next to quantum sensors, in the lab, it is just the particles being controlled. So the boundary between computers and quantum sensor is just arbitrary. So instead of arguing that our advantage is computational advantage, we decided to do more scientifically meaningful task, which is trying to figure out what makes our protocol qualitatively different from conventional protocols. And the short answer is we were able to characterize and rigorously say coherent quantum information processing is needed in 3 different aspects. But today I'm going to talk about one aspect, it's a nonlinear, non-perturbative approach. So in usual quantum sensing, our aim is to prepare a quantum state that depends on the signal. So that when the signal strength is 0, you prepare psi 0. When signal is weak, you perturbatively change the quantum state so that it has some perpendicular component with the prefactor scaling factor alpha. Therefore, we want this to be as sensitive by maximizing alpha. In fact, this alpha is a value that parameterizes so-called the quantum Fisher information. We want to make sure the quantum state is changing, it's very susceptible to the perturbative signal. So in order to solve this AC sensing, we should make sure this coefficient by B mean, the minimum detectable signal, is detectable size, like order 1, and we demand that for all frequency of the signal. So that means Fisher information should be reasonably large when it's integrated or averaged over frequencies. Turns out, we were able to rigorously show that any protocol that satisfies these conditions must have time that's conventional scaling. That means any perturbative approach, any approach based on quantum Fisher information necessarily takes the time that's conventional sensing. Another corollary of the results is that any protocol that saturates Grover-Heisenberg limit must have vanishing quantum Fisher information. So non-perturbative approach is needed. So for these problems, these type of problems, quantum Fisher information is of limited use, and that's one of the aspects that qualitatively distinguishes our work from for conventional sensing. So let's move on to the next part, the near-term experiment. So far, I explained as if our approach requires very sophisticated quantum control. But turns out, if our aim is to do a proof of principle demonstrations, we can have an amazingly simple implementation you can consider. So that's what I'm going to explain. Turns out, if you have a central spin model, so imagine you have one particle that I call sensor, and the surrounding particles, like spin particles, that I call computers. And then you have Hamiltonian of this form. That means sensors has a transition frequency omega s. And we have an Ising interaction between the sensor particles and qubit register. I assume like there's NQ qubit registers interacting with the Ising interactions. And you have a single qubit control for the sensors. And that's all you need. Based on this central spin model and the dispersive Ising interaction and single qubit manipulations, I'm going to show you can already do proof of principle demonstrations. And this Hamiltonian appears universally across different atomic systems, because if you do the perturbation calculations, the leading order energy shift is always a dispersive, these are Ising type interactions. So even though I model it in terms of spin system, exactly the same thing can be pursued in the cavity systems with the continuous variables. So how does it work? So the key idea is the following. Let's rewrite this Hamiltonian. Let's assume this Ising coupling strength, Ji, is different for every pair of particles, between the central particle and the qubit. Then you can rewrite in this way. So here, this is the sensor particles, and this K is a binary representations of this rest of the qubit registers, the 0-1 configurations. And you can understand that depending on the binary configuration of the rest of the qubits, the transition frequency of the central spin is changed. So the energy level diagram looks something like this. Here I'm along x-axis, I'm enumerating configuration of the register qubit, and the bottom band is the sensor qubit being up, and the top band is the sensing qubit being down. And they have a different transition frequency depending on the configurations. So idea is we prepare the superposition state of all the bottom band, and imagine for the proof of principle demonstration that the signal frequencies happen to be resonant to one of these perfect transitions. Then, by waiting for exactly the right amount of time, you apply 2 pi rotation only for that particular configurations. And if you have a 2 pi rotations, you pick up phase -1, and that's exactly the Grover operations that we want. Therefore, we can achieve superposition sensing and Grover reflection operators simultaneously simply by waiting under the signal, in the simplified assumptions that the signal is happen to be resonant to one of them. Okay. So we try to be a little more quantitative of these proof of principle protocols based on MV center settings. So MV center is particular solid state defect in diamond. Yeah.
Can we just go back for 1 second to
Yes.
say, so Z hat S, is the spin along a particular direction, or what is it? What is the?
Yeah, so I don't change the notation. These are sigma Z operators, like so Z rotations.
Okay, and then when you have two of them, is it the dot product between the two spins, or is it still each one along a particular?
So it's a sigma Z operator, two-body operator.
It's
So
dot
dot product, yeah. But it's not a vector operator. So like a ZZ component. So
easy.
the only the ZZ component, yes. So it's it's like Ising coupling. Yes. Any other questions? Yeah.
Like you need to know all these frequencies, and you need to be sure that they are distinct.
Yes, for this proof of principle demonstration, I'm assuming two things. One is the range of frequency is no longer continuous, but one of the discrete set. That allows us to prevent implementing all this digitization idea. And also we are assuming the strength of the signal is either zero, so signal does not exist, or weak but known value. Because it's known value, we can wait for exact 2 pi time. So that's the simplifying assumptions, and I don't think it has any practically useful applications if you formulate it as it is, but rather we can do the proof of principle demonstrations of performing superposition sensing and Grover search over different frequency values. So this is somewhat solvable limit. Okay, so we consider the proof of principle demonstrations based on this by numerical simulation. What I have done is we have electronic spins of nitrogen vacancy color centers. Like it's known to be a good quantum sensor. So that's why we chose this particular platform. And naturally, nearby carbon atoms have nuclear particles, nuclear spins, spin 1/2. And we are going to use that as if it's a quantum computer. And their hyperfine coupling is such that in the dispersive regime, you naturally realize the Ising interactions, like the level schemes like this. So it turns out we can develop the pulse level implementation. So our Grover algorithm in this simplified case is exactly applying the signals for a certain durations so that you implement the oracular operations. Or you apply another 2 pi rotations to implement this init state reflection operations, and it's to alternate between them. So our protocol is literally applying 3 pulses, like pulses, and repeat. And that simple protocol is already achieving our proof of principle demonstrations. So we did a numerical demonstration of how much gain you can obtain for numerical simulations. We put in the coupling strengths of Ising interactions based on experimentally measured value for the leading group in the world from Delft. And then we put in the coherence time of the particles, conservatively estimated. However, the estimated from the real world experiment. And we tried several values to see where we are at. And what we have computed was, imagine you do our approach versus a conventional best known approach and take the ratio of the time it takes. So this ratio large means we have an improvement. We have a shorter time for our algorithm, so that's improvement. What it shows is that different curve corresponds to different coherence time that we assumed. For this one is most optimistic, but the not so crazy estimate of the coherence time. And x-axis is a target strength of the frequency. And then we see that already with the near existing technology, we can achieve about factor of 8 improvement in accomplishing the same task. This is a different way of plotting the same thing, the improvement as a function of number of register qubits you probe. And you see the exponential growth because when number of register qubit increases, the number of frequency that you can probe in superposition grows exponentially. However, when the coherence time is not so good, like this curve, it comes down because even though in principle you can probe simultaneously, our algorithm cannot be finished within the coherence time. That's why it goes down. So in the limit coherence time is very large, you can go all the way up. Eventually come down due to limited coherence time. Roughly speaking, the improvement factor depends on the coherence time of the collective spin degrees of freedom and the target strength that we are to probe. So with that, let me move to the discussion and outlook. I only have a couple more slides. So one aspect is our realizations of what we call a nature as oracle. So I already mentioned at the beginning, this concept of oracle is a very important conceptual tool in computer science, because by assuming you have access to oracle, you can distinguish what type of task quantum computer can do better compared to the classical computer. However, often it's a theoretical exercise. Who gives you the oracle? Like, you should just assume that we have access to that. So it's not oftentimes not relevant to the real world, like practical implications. However, we are changing the viewpoint. We take this oracle as if some subroutine developed by quantum sensing. So in a sense, the nature is providing our oracle, such a way that we can do certain tasks. In this point of view, the very task is interacting with the nature and sensing. Therefore, assuming we have access to the oracle is valid. The only task we need to do is nature gives us the oracle in some form that's maybe not ideal. We need to transform them into the form that we well understand. In this example, we talked about Grover algorithm. So this is good, outlook. So maybe computer scientists should explore this direction more. And the second idea is this. Throughout my talk, I intentionally ignore the discussion of the decoherence and error. Our protocol has a certain level of robustness in decoherence. So adding some decoherence does not kill the quantum advantage. However, it's not as robust that I hope for in terms of quantitative scaling analysis. And that's partly because we have a fundamentally limited understanding of how to make an interface, robust interface between quantum sensor and computers. In modern days, my phone or these computers, if you only have keyboard and screen, it's not as useful as what it is. It does have other input-output interfaces like camera, speaker, microphones, and when they are operating together, we can do much more tasks. But this type of study has not been done, to my best knowledge, in quantum computing. How do you robustly take input and output? But this is fundamentally in tension with the idea of quantum error correction. The quantum error correction is a technique to kill all the unwanted noise, and that's needed for the developed large-scale quantum computer. But if you want to integrate quantum sensors, it could be that you accidentally kill the signal that you want to detect by treating them as if it's a noise. So what I mean by this logical quantum sensor is some kind of new ideas that tells us how to kill noise while keeping the signal. There must be some concept that fundamentally separate them out. And also ideas such as like superposition sensing, how to make them robust. But this set of ideas needs to be studied better. So to summarize, our history have evolved around like sensing. At the beginning, we were using like naive, like compass, like so-called like classical sensings. But if you try to improve this sensing better and better, at some point you hit the fundamental limit. That is that our measurement tells you the discrete outcome coming from the quantization of energy levels. And that corresponds to quantum limit, so-called the standard quantum limit of sensing. But we can go better than that. By entangling them, we can actually leverage and improve sensing further beyond this quantum limit, so-called the Heisenberg, all the way to Heisenberg limit using entanglement. I hope that I convinced you that going further in the future will be quantum computing enhanced sensing, where nonlinear, non-perturbative data processing of information happens in real time for the sensors, so they go even further. Thank you so much for your attention.
Oh, we have time for questions? Questions for Soonwon? Yes.
As your output down depends on the primary knowledge of your frequency distribution. Like you have a flat distribution of your frequency, ranging from for example, phase regime 0 to 2 pi. But if I have some distribution like Gaussian for double peak, does it can you find that maybe some even better improvement?
That's right. So turns out the optimum is still our approach. However, when you do the parallel, the superposition sensing, when you do the Grover algorithm, you do the different rating. So the amount of improvement will be different. It's very similar to the settings where coupling strengths depends on the frequencies. But yes, absolutely, we can do sometimes better by leveraging the prior knowledge of the probability distribution.
This is just like more or less like the faster.
No, sometimes it's a scaling. That's right. But that's also saying for just general search. Suppose you have a bunch of boxes. You are asked to find a marked element. But somehow you have a prior knowledge and the probability distributions where there's more likely, box. The classical strategy is to open box one at a time, starting from the most likely to the least likely, right? So that's the best approach. And best quantum approach is also very similar. Just order them and then do the quantum search on top of that. And that sometimes change the scaling behavior.
Other questions? So Soonwon, so your remark at the end about logical quantum sensors. So do I understand that your work has not ruled out the possibility of a quantum sensor which is robust against noise and can still achieve the quantum computing enhanced advantage?
Yeah, I don't know the answer. So it is possible that under certain noise model, this vague idea of what I call like logical quantum sensor might be not possible at all for some fundamental reasons. That'll be sad, but that's what it is. In fact, related results exist in terms of improving sensitivity, like improving like sensitivity, entanglement-enhanced sensitivity. If you have a certain noise, it's probable that you cannot enjoy sensitivity enhancement. But our advantage is originating from a different aspect, and namely the Grover aspect. So the key question is whether you can improve Grover search, okay, perform the Grover search, even when the Grover oracle is somehow not perfect or noisy. And that's why we are very actively working on. And still, we don't know the answer, whether this particular approach can be made robust or not.
Wait.
So you framed it in what's the time it takes to measure some minimum B field, but originally you posed it as I have 6 U's, what's the minimum B field that I can sense? But with decoherence, there's also like a time limit. So you have to break your sensing problem into smaller pieces and compose them. But since your algorithm has vanishingly small Fisher information, is there any prospect to how you compose the algorithm multiple times, like when you have a finite time limit due to some dissipation rate or something like that? Is there some?
Yeah, that's right. So if I have a coherence time, the minimum you can do is the following. So I do not do the search, quantum search over the all frequency bin, but only do the quantum search around the subset of the frequency bins so that this search terminates within my coherence time. And then do the classical scan for the next chunk of the frequencies. That approach is already better than just sequentially searching the conventional method. And in that sense, we have a partial advantage. But my personal belief is that we can do maybe better than that. So in some sense, sensors are used for oracle like construction, and then it's reset to the initial state. And that's an opportunity. So my hope is that as long as coherence time is longer than single construction of the Grover oracle, then you somehow robustly construct the multiple Grover oracles and then enjoy like a Grover speed up. So that's way better than this naive approach. And that's my ultimate aim and the realistic ultimate aim, but we couldn't solve that yet. Yeah, let's see. Yeah.
Soonwon, I am sensing that your audience is awestruck by your very interesting talk. I'm also sensing that it is time for us to adjourn to the reception where we can continue to enjoy interactions with the speaker. Soonwon's IQIM seminar tomorrow at noon in 114 East Bridge is on computation protected phases of matter. Let's thank Soonwon once more for this.
Thank you.